This is a presentation of the implementation and conclusion of our project for this semester, presented by Wesley, Scott, Quinten, Allen, and Hudson Topping. The purpose of this experiment was to demonstrate how deep learning algorithms can make the cybersecurity field more effective and accurate.
This data from what users of a program are expected to do will establish a baseline from which we can interpret malicious data using deep learning and neural networks. Everything will be open to observation by the neural network. We will choose not to limit with consent from the users. We will choose not to limit the neural network to only, for instance, the choices that are made, the pages which are opened. A malicious software can reveal itself through faulty IP addresses or suspicious VPNs, or even the speed at which it's able to move through pages which no ordinary user would do, no non-malicious user would do. So we will need to establish regular activity through users. First, we will use the software ourselves as the developers to build an obvious database to allow the activity before opening it to random users to serve the defined program. Once these foundations have been set by us first and then by general users, we will have a good metric about what ordinary activity is and what we should and should not punish and lock out and defend. We will do this through a combination of four measures: the cost of a disgruntled user, the cost of a successful malicious attack, the rate of a wrongly turned away user, and the rate of a successful attack. We will then create a mathematically perfect degree of specificity which minimizes risk and maximizes satisfaction.
In order to test our neural network, we set up 3 different test case behaviors to compare the algorithm speed to human detection speed. In the first test case behavior, all visit locations are in close proximity, i.e. someone who lives and works and maybe goes to school in the same area and doesn't travel very much. The second case behavior, all visit locations are contained to 2 specific regions, i.e. someone who commutes to work and lives far away from there, or maybe they live and work in one area and they travel very far to their parents, but it's contained to those specific regions. The third test case behavior, visit locations are constantly changing, i.e. a business person who, but they stay mostly in one region, like a continent or country, i.e. like a business person who is traveling all over like Europe or Asia or something like that. And then 30 different accounts were set up, and each was assigned one of the 3 different behaviors at random. Each of the accounts was set to log in 30 different times, and that way the 30 different login times was able to feed into the algorithm. It was able to give it the algorithm's efficiency was simple, it was fast, it was very accurate in its profiling. It was made absolutely 0 errors as opposed to the human calculations, which made some errors. It was able to profile the difference between the malicious users and the innocent users in an amount of time that was basically 0. It was so negligible, and this makes it much more efficient than human checking. This is as opposed to human efficiency. The average time to detect errant visit locations for humans for the first behavior set was 5.4 seconds. This is the behavior set that was all in one single location. The second behavior set, that was 9.0 seconds. This was the behavior set that was in 2 different locations that didn't vary outside of those 2 locations. The third behavior set, it took 22.1 seconds. This was the one that varied across one continent or one region. It took 22.1 whole seconds for a human to identify an outlier, as opposed to an algorithm which took less than a second in each circumstance and made 0 errors. In addition, humans, our team, the team members who tested this themselves, made errors with respect to behavior set 3, there was, I don't know if there was one or two, there was instances in which things were marked correct when they should have marked incorrect. It also took a lot of time, effort, and concentration. In conclusion, the use of the algorithm was much more efficient than the use of human power to check each and every visit location to make sure that there's not malicious intent. It should be noted that we made sure that the external variables going into this incident were minimal, so the neural network was able to perform very easily. It didn't take a lot of work. But even given that, the 22.1 seconds to less than a second ratio was very much worth it. Like I said earlier, human checking is impractical. It takes time, it takes effort. And neural networks, all of this goes to prove that neural networks can and should be trained to predict and ensure the security of online network and to prevent